So this video is going to cover how to do a complex between subjects ANOVA. So when we talk about complex ANOVAs, it's basically where we have two or more independent variables in our data set. This is actually just based on an extension of what we did in the univariate ANOVA lecture. So the example is the same, but we just added another independent variable to it. So we can see how this additional independent variable impacts our study. So if you refer back to that video, you'll see what we were interested in is whether exposure to different body weights affects subsequent ratings of the acceptability of an overweight body shape. In this experiment, what we're doing is adding another independent variable. So if you'll recall, we were showing people lots of pictures of individuals who were either obese, overweight or underweight. However, the researcher may be interested in what is the impact of the quality of the picture or the level of detail in the images on this effect. So what they did, they added another variable called colour level, in which pictures were either shown to individuals in full colour, black and white, or just a silhouette of an image. And they believe that we will see the impact of the different weights on the acceptability of the target weight, but only when the pictures are in full colour. So only when they're a realistic representation of what a person looks like. Less effective when they're black and white, and even less effective when it's just purely a silhouette. As you can see, our dependent variable is exactly the same thing. This person is an unacceptable weight, and we score it from 1 strongly disagree to 7 strongly agree. So if we look at our data set, what we can see is we've got our dependent variable target acceptable, which is just the ratings on the target acceptability scale, and our independent variables are labelled here. So if you look at our data set, what you can see is we've got target acceptable scores here, our dependent variable here, and then our two independent variables are labelled here, and they're just simply labelled by the numbers of the conditions. So for picture weights, we've got condition 1, which is obese, condition 2, which is overweight, and condition 3, which is underweight. And you'll see this sort of repeats. And then we've got colour level, so all the 1s here are exposed to full colour, all the 2s here, these are exposed to the black and white image, and finally all the 3s are exposed to the silhouette. To analyse this data, it's a relatively simple procedure to do these forms of ANOVAs. It's not as complicated as when you have within subject designs. Simply, we just go to Analyse, General Linear Model, and then we go to Univariate. And this gives us our univariate ANOVA window. And it's a very straightforward thing. We've got a single dependent variable that we can put in there. Of course, that is our dependent variable. This person is an unacceptable weight. Then we've got these boxes. We don't really need to worry about our random factor box at all, nor the covariates, because that would be an ANOVA, which we'll be covering in later videos. What we simply need to do is what the fixed factors are, or our independent variables. So we just simply need to click those across. We could click run now, and it would actually give us an ANOVA. However, we should ask for quite a lot more information. So we need to click on options. If we go to options, we get this window. We want to ask for our descriptive statistics. This will allow us to make our descriptive statistics table, and of course estimates of effect size. This will give us a partial letter squared for our main effects and for the interaction as well. And we want homogeneity tests. We need homogeneity tests so we know we've met the assumptions of the ANOVA. We also want this as well. We need estimated marginal means, and we want to see them for picture weight, colour level, and the interaction between the two. Remember that an interaction is what is really, really critical, because this is ultimately what we're expecting. We believe the effect of picture weight of this independent variable on our dependent variable is dependent upon colour level. So we believe that this effect will only work when we have a full colour picture. and this interaction is critical to us. Now we also want to compare main effects, and then we can do our confidence interval adjustment if necessary. So we've got the least significant difference test with no adjustments. In this case, we'll ask for a Bonferroni correction. The Bonferroni correction will correct the p-value that SPSS calculates by multiplying it by the number of comparisons made. So for the main effect of picture weight, this is 3 levels, and we've got 3 possible comparisons here, which is obese compared to overweight, obese compared to underweight, overweight compared to underweight. So SPSS, when correcting for multiple comparisons, when looking at the main effect of picture weight, will multiply any calculated p-value by 3. For the interactions, this is a bit more complicated, and again it's going to do actually a lot more corrections, but we'll come on to that later on in the video. So we select all the things there, so we can click continue. We can also ask for our plots. This is a simple way of visualizing more complex data. You would never use these graphs and put it in a report because they will be lacking error bars, but they give you just a good overview of your data and can help interpretation if you're getting a bit confused by all the numbers. So we'll ask for horizontal axis can be picture weights, separate lines can be color level. And we need to click add. If you don't click add, it won't produce anything for us. Click continue. And then that's all we need to ask for. So we can click on OK, and this gives us our output. So the first thing is just how the between subjects variables are labelled. So picture weights 1, 2 and 3, colour level 1, 2 and 3, and how we've labelled it. And we also get shown the number in each condition. As you can see, it's not a perfect balance in each condition, but there's a good number in each condition, and they are pretty much relatively balanced anyway. There's not a great deal of difference, those two conditions being the most different, but nothing that would have any real effect on the data. It's nothing to be concerned about. The next thing that we see is our descriptive statistics table, and this gives us all possible descriptive statistics for this data. So when pictures are obese, this is the mean and standard deviation for the coloured pictures, obese black and white pictures, obese silhouette pictures, and these are the number of peoples with each of the sub conditions as well. So you've got 12 people who are exposed to obese silhouettes, 16 people exposed to obese black and white, 17 people exposed to obese colour pictures. Then it repeats over for overweight, underweight and so on. The total score here is, this is the mean and standard deviation of responses to obese pictures regardless of what the colour level was, and that's the same here as well. So that's the mean and standard deviation of responses to overweight pictures regardless of the colour level. This total one here is slightly different. So this is regardless of picture weight. This is the mean and standard deviation of the response to colour pictures regardless of the weight. So essentially it's collapsing conditions. Mean and standard deviation of response to black and white pictures regardless of weight, and the same for silhouette. And this final total here, think about this, the total under total, this is just the mean and standard deviation for the whole sample regardless of any independent variable at all. And you can report these in a descriptive statistics table. A nicely formatted table would look something along the lines of this. The next thing you want to look at is, do we meet our ANOVA assumption of homogeneity of variance? As you can see, our Levene's test statistic is non-significant, so this means that we do have homogeneity of variance within this data set. So that's good. We can continue with our data, and we can accept, we know what's coming out of this table is going to be fairly robust and valid. Just remember that we want these ones to be non-significant. We want these tests of ANOVA assumptions to be non-significant, so to show non-violation of the assumption. This is our test of between subjects effects. So this table, test of between subjects effects, is basically where we got all our ANOVA statistics from. This will tell us whether we've got a main effect of picture weight on our dependent variable, a main effect of colour level on our dependent variable, and whether there's an interaction between picture weight, and colour level on our dependent variable. So let's go through each one at a time. So the first thing here, picture weights. So as you can see here, we have a significant main effect of picture weights on ratings of this person is an unacceptable weight. And we'd write this up accordingly, taking our degrees of freedom. From there, our f value, our p value, and our partial letter squared. Colour level, this also has a statistically significant effect on participants' ratings of the target picture. So you can see, we take our degrees of freedom, f value, p value, and partial letter squared, and write it up accordingly. Now importantly, we also see there's an interaction between these two independent variables influencing our dependent variable. And as you can see, again, that's statistically significant. We take our degrees of freedom from this point of the table as well and write it up accordingly. So this is all very well, but as we know from previous weeks, just saying there's a significant main effect of an independent variable is not enough. This just merely says, for example, that colour level in some way influences responses on that dependent variable. It doesn't say which colour levels significantly differ from each other. We need to do further analysis to work that out. And of course the same thing applies to picture weights and the interaction between the two. So starting with picture weights, we know we've got a statistically significant effect, so this means we can look at our pairwise comparisons in more detail. So this is our pairwise comparison, and as you can see, it's been adjusted for multiple corrections. We asked for a Bonferroni correction. So what does this table tell us? Well, participants exposed to obese pictures compared to overweight pictures showed no statistically significant difference. This is regardless of any colour level. That variable no longer counts. Obese versus underweight, however, are significantly different from each other. So people who are exposed to the obese pictures compared to the underweight pictures were significantly different in their rating of this person as an unacceptable weight. And as you can see, those exposed to underweight pictures rated the individual in the target picture as being a more unacceptable weight than those who are exposed to the obese pictures. And you can see it's statistically significant there. Finally, there's no significant difference between the overweight and the underweight condition. So that significant main effect that we saw in the ANOVA is driven by this one single difference here, the obese underweight comparison, and we'd write this up accordingly. You can just refer to the descriptive statistics in the table, or you could refer to the estimated marginal means. Now these means differ from the means in the descriptive statistics table. There's just a simple reason for that. These means here are produced after controlling for the effect of the other independent variable that's not included. So this is also corrected for the colour level. So they are produced after controlling for some of the variance associated with colour level, and that's why we call them estimated marginal means. They're not normal means, they are estimated after controlling for the other independent variable. So we know from this that we've got a significant main effect of the picture type, and we know that's driven by the obese underweight difference. However, we also need to look at our colour level main effect as well. We've got a statistically significant main effect here, so we need to look at that in more detail. And we just follow exactly the same process here. So these are colour level, again estimated marginal means. This time they've been corrected for the other independent variable, the picture type, the weight of the individuals in the exposure pictures. And if you can see the comparisons here, colour versus black and white, there's no significant differences between these two conditions. So if you show people colour pictures or black and white pictures, it has no effect on this person as an unacceptable weight dependent variable. Colour versus silhouette, however, is statistically significantly different, and that's because if we see colour pictures seem to have an effect on our dependent variable in as much as they are rated more unacceptable if someone's seen the colour pictures compared to the silhouette pictures, and that difference is statistically significant. This is completely regardless of actually the weight in the picture, just the colour level. The final comparison is just black and white versus silhouette, and there's no statistically significant difference between the two. So that's all very well, but actually the most important and interesting thing that we're actually looking at is this. This is the interaction between the two, because our hypothesis states that the picture weight will only have an influence when the colour level is full colour. Only under that level of the independent variable will this produce any effect. That's what we predicted. So if we scroll down, we can see we've got estimated marginal means here for obese colour, obese black and white, obese silhouette, overweight colour, and so on. However, you'll note, unlike say these tables here, there's no p-values given. You can get SPSS to do these for you, and I'll show you that in one moment. First, let's have a quick look at the profile plots. If you look at these profile plots, you can see this does quite clearly delineate what effect's going on. So we've got, you can just about make out there, this is the silhouette, green line is black and white pictures, and the blue line here is for the colour pictures. And as you can see, when there's been exposure to obese individuals, there's almost no difference whatsoever in the ratings of this person as unacceptable weight. Now, you see a bit of more of a difference starts to appear here when there's no overweight pictures, because the silhouettes pictures seem to be pretty flat along the bottom. There's no great ratings of this person unacceptable when the picture is silhouette. The colour and black and white pictures are pretty similar to each other. And now what we can see here is quite a big divergence in the conditions, in as much as there's clearly a much higher ratings of this person unacceptable weight when pictures are underweight and it's in colour. If you look at the green line here, this is much lower down. This is when the pictures are underweight individuals and they are black and white. And then at the very bottom here, it doesn't seem to have any influence. Even the pictures are underweight, it has no influence when they are silhouettes. However, what we can do is we can look at this in more detail and produce some probabilities to tell us which conditions significantly differ. However, we can't produce any p-values through the normal menu system in SPSS. What we've got to do is almost trick SPSS into doing it for us. It's a relatively straightforward process though. So we just go back to our univariate ANOVA, just as we did before, and you can see it's already set up for us. If you haven't closed SPSS, it just saves the last thing you did. And then instead of clicking OK, we click this button, which is called Paste. And this opens a syntax file. This is basically the programming language SPSS uses. And we need to add something to this programming language to make it work, and it just really involves copy and pasting. So what you can see is, you can see almost recognise the sort of commands. Estimated marginal means, we want tables, picture weight, and we want to compare them, and the adjustment is a Bonferroni. And then we want tables with colour level, and we compare them using an adjustment that's a Bonferroni. And now we've got a table, picture weight, colour level, but it doesn't ask for anything else at this point. So what we can do is we can tell SPSS to do comparisons. Simple way to do this is you can just copy and paste that to there, because you don't have to be spelling Bonferroni correctly and so on. If you make an error, it will not run at all. It'll just give you a difficult to decipher error. So, and then we just write, if I compare, you can just write picture weights. So this command basically says I want you to split it down by picture weights and then do the Bonferroni adjusted comparisons. So then all we have to do is highlight that, click the green triangle. This reruns your entire ANOVA. Nothing will change. All these figures are exactly as they were the first time. However, if we scroll right down, you can see now it's given this rather horrible looking pairwise comparisons table. So what's this done? So we've now got colour level listed here, colour, black and white, silhouette, and then picture weights listed here, obese, overweight, underweight, and so on. This is doing all the comparisons that we now need. Just remember with these tables, it does everything twice. For example, colour pictures, obese versus underweight, colour pictures, underweight versus obese. It does everything twice, so we only really need to look at half of the figures in this table anyway. So, what's this actually showing us? So, when pictures are full colour, obese versus overweight pictures do not differ. When pictures are full colour, obese and underweight pictures do significantly differ from each other. When pictures are full colour, overweight and underweight also significantly differ from each other, and that's the three possible comparisons between the weight categories: obese versus overweight, obese versus underweight, overweight versus underweight, when pictures are in colour. So we can see we've got these two statistically significant differences, which are the obese underweight comparison and the overweight underweight comparison, and we see that effect when pictures are colour. Now if we look at the black and white pictures, obese versus underweight don't differ, obese versus underweight don't differ, overweight versus underweight don't differ from each other as well. So when pictures are black and white, we don't see any significant differences in the weight exposure conditions. Finally, silhouette, again, same thing, obese versus overweight, no difference, obese versus underweight, no difference, overweight versus underweight, no difference. So this interaction is being driven, as predicted, by the fact that when pictures are full colour, we see the effect of weight exposure. Obese, underweight significantly differ, overweight, underweight significantly differ, but there's no differences in this whatsoever when the pictures are not in full colour. So the effect of weight exposure is dependent upon the pictures that we use in our experiments being more realistic, being more what people see in the natural environment, and we just write this up accordingly. It's important to note that because there's only two significant results out of all possible results, which is 9, because you've got 3 comparisons within each level, there's no point reporting loads and loads of non-significant results. We can just simply say no other significant differences were found.